Hi. Today I'll show you a couple of things about cosmology type space-times and the Big Bang and a couple of other things like that, and sort of like the mechanism by which these things are studied and dealt with. Alright, so let's say we have the following. Imagine you had this this thing right here, which is gonna represent the space-time, and imagine this extends in all these directions like this. So it's not just a square, it just keeps on going. Alright, it may not, it doesn't necessarily need to keep on going. It may have like a cutoff point, let's say down here or something like that. For example, that would be the case of the Big Bang. Alright, now the metric for this thing, and by the way, most of these can be treated with a drawing, so it turns out that this is what they call the Fermi-Robertson-Walker spacetimes, and they're pretty uniform, so you can sort of encapsulate them with this drawing here. This vertical vector and this horizontal one, you can imagine putting a copy of this anywhere along here, along the space. Alright, now we have a metric, and a metric, it can be represented by a matrix, right? Or you can just have this thing, this G, okay, that varies from point to point. There'll be a G at this point, there'll be a different at this point right here, there'll be a different G at this different point, etc. So let's say we call this point P, this point Q, right? So G at P, this vertical vector, is going to be -1, and G at P, this horizontal one, is going to be A of P, which you'll often see as A of T. We'll see later why, because these points P basically have a time associated to them, sort of like a global time in this model, which time is not always global, but when the model's got enough symmetry, and so on and so forth. Oh, and by the way, GP of this is equal to 0. Just specifying in this two-dimensional model the behavior of G on these vectors is enough to specify fully the G. Alright. Now, turns out that, okay, this vector here is one specific vector. Where's the other color? This vector here is one specific vector. So we must have, it could have been this one, this one, this one. Could have been longer or shorter, okay? So, but once you fix that vector, this gives you -1. It basically tells you that if you had a curve, let's say, who had this as its tangent vector, okay, if you had a curve who had that as its tangent vector, then that curve would be parametrized by arc length, what they call arc length, except that since this is relativistic, you get negative numbers for the arc length, because this is what is called a time-like curve. Time-like curves are things like this, and then light-like curves, or light-like vectors rather, I should say. This is time-like vector. Time-like curves just have their tangents being a time-like vector, and light-like curves have their tangent being a light-like vector. But a light-like vector is just a vector whose g like this of it with itself would give you 0. Okay, and those represent the paths of light rays, or the instantaneous for velocities of light rays. Okay, so now again we have this. Alright, so one such curve that has this as its tangent vector all the time are these vertical lines. Right. These vertical lines right here. Alright. The next thing I want to show you is basically that these vertical lines are geodesics according to this metric. Okay. Now why is that? Well, look at this. Pick a point here, any point. Let's pick this point right here. Okay. Let's pick that as the tangent vector. This right here, same thing. Uglier drawing, but same thing. Alright. Now, imagine that you had a curve that did this. So it's a curve through this point with that tangent vector. Okay. Upon flipping over this line, okay, that curve now looks like this. Right? But the thing is this, that for a reason I will not explain to you fully here, right? That flip, first of all, is a symmetry of the metric. This you may be able to prove with the information that I've given you here, but that's not what I'm not going to cover here. What I said I wasn't going to explain to you fully is the following, that if something is a geodesic after such a symmetry, the resulting curve also has to be a geodesic. So then there would be two geodesics through this point with this as a tangent vector, and that cannot be. There's a theorem that, from differential equations that says that through any point there exists a unique through any point with a given tangent vector there exists a unique geodesic. So alright, so we've proven that these are time-like geodesics. The next thing you may want to know is the following. Okay, the next thing you may want to note is that these are geodesics, and in the energy momentum tensor they show themselves to be basically the history in space-time of a dust of particles, let's say, and had you two of these together, they could be like two nearby galaxies or something. Typically the distance between them is very large, right? And you may want to somehow model, okay, that the distance from here to the next guy just is this vector right here. Now, if you already have a parameter on this curve, and we know that there are parameterized by arc length, etc. Okay, and by the way, arc length is just the passage of proper time, so it's the actual time measured on clocks that this guy right here, whose history is this world length, would measure. Then let's say that you had the times like this. This is time 0, this was time 1, time 2, right? Alright. Then when I was telling you this right here, this A of t actually corresponds to that. It's the A of p, but for the particular point p that has a time associated to it. So that A of t is that. Okay? So it could be either A of p, but you know that p has a time associated to it, or A of t. Alright. And let's say that now that this A of t happened to be e to the t. So this, right here, has associated to it e to the 0. This has associated e to the 0 with a 0 down there. No, the 0 goes in the exponent, sorry. E to the 2, right? Okay. But remember that the length of a vector is the square root of g, the vector like this. Okay, so for this one, the length of this vector right here is actually the square root of e to the 0, which is 1. For this one right here is the square root of e. For this one right here is the square root of e squared, which is e. So you notice that the vectors, as you move up this way, are getting longer. Okay, so this is an example. This is an example of how basically how space-time is expanding. For example, so in a model such as this, you know, the space-time would be expanding, and this guy would see the other guy as moving far away. Now keep in mind one more thing, and it's this, that this picture here is a little bit inaccurate because of this. This space-time is generally curved, so you have this situation right here. So you have it like this. So these vectors that I pictured here are actually these tangent vectors here. So then whenever you have one of this line and another line, it's like this. So these vectors don't really touch from this line to that line. See, they're sort of like that. So it's sort of a naive idea that they would actually represent the distance. Okay? And that's it for this video. I will continue later on.